With exponential functions, a certain fixed base is raised to a variable power, producing a continuous calculated result. Since an exponential function is one-to-one, that is, each x value corresponds to exactly one y value, and each y value in turn corresponds to exactly one x value, it follows that we should be able to find an inverse to the function. Let's set up the concept first this way. If an exponential function has a fixed base raised to a variable exponent to produce a specific resulting value, shouldn't we be able to find the exponent if we have the base and that resulting value? This operation, the inverse of an exponential function, where we find the exponent given a certain base and overall value, is called a logarithm. A logarithm is simply a system or mechanism for finding a particular exponent in an exponential situation. For a given exponential function where a base b raised to the xth power is y, the corresponding logarithm is, in proper but slightly awkward terms, log base b of y is x. And no, not that kind of log. Again, this base has to be a positive number and preferably not 1. But instead of the domain being all real numbers, the domain must also be a positive value, as all results of exponential functions are positive. The range of a logarithmic function is all real numbers. Some basic examples of logarithms. Since 2 to the 4th power is 16, log base 2 of 16 is 4. If 1/3 to the 2nd power is 1/9, log base 1/3 of 1/9 is 2. Checking the result of a logarithm is simple. Take the base, raise it to the result of the logarithmic operation, and be sure it matches the value in the logarithmic expression. The graph of a standard logarithm is the reflection of the corresponding exponential function over the line y equals x, with an asymptote at x equal to 0, and a progressively slower climb in y as x increases. In the same way that 0, 1 was the anchor point for exponential expressions, 1, 0 is for logarithms. As with exponential functions, all standard manipulations work in what are now expected ways. A note on notation. When you see a logarithmic expression without an indicated subscript base, the base is 10. So, for example, log 1000 is a simpler way of writing log base 10 of 1000, which in either case is 3. Base 10 exponential and logarithmic functions are very common in science and physics studies, where the effects of exponential growth are in play, such as acoustics, where perception of volume is a logarithmic function, and geology, where the earthquake grading Richter scale is a base 10 logarithm. There is also the matter of ln, the natural log, again, not that kind, which is the inverse of the exponential constant e. We will discuss this separately soon. Because of the way exponents work, logarithms have a number of interesting trig operations rules that we can use in certain situations. For example, given two logarithms with the same base, log base b of m plus log base b of n is equal to log base b of m times n. Log base b of m minus log base b of n is log base b of m divided by n. Please note that log base b of m divided by n is not log base b of m divided by log base b of n. We'll get to that form shortly. Also, log base b of m to the nth power is equal to n times log base b of m. Although these are perfectly legitimate exercises of the rules of exponents and logarithms, they can sometimes feel a little bit like mathematical sleight of hand. Much more useful is the base change operation. Any logarithmic expression in the form of log base a of n can be rewritten with a different base as log base b of n over log base b of a. This is extremely useful when solving problems on calculators that only offer fixed base 10 logs or ln's. For an example of this, let's go back to our certificate of deposit from the prior conversation. Suppose the bank offers an option to let the depositor keep the cash in the bank indefinitely under the original terms. How long would it take for the standing value of the account to double from the original $5,000? Let's set up our original expression loaded up with all the same values. $5,000 6% per year, and 12 compounding periods per year. How many years will it take for a, the current value, to equal 10,000? First, we can simplify the 5,000 out from either side. We only really want the multiplier, 2, as a result of these operations. 2 is equal to 1.005 to the 12t power. So our base is 1.005, our result is 2, and we are finding the exponent. 12t is equal to log base 1.005 of 2. Since it's unlikely at the least to have a calculator button preset to log base 1.005, we can instead take log 2, that's log base 10 of 2, over log 1.005, and the answer is 138.9757, maybe 1 day short of 139 months. Divide this by 12, and we get 11 years and 6.97 months, again about 1 day short of 11 years and 7 months. This is only a simple application of logarithms. We will get into much more involved and relevant models, including one involving pizza, next time.